Okay, so Jerome's going to walk around, make sure you are being ethical and honest. This is what it means. Okay, so here's how the point breakdown goes. You have to mention the raise. That's 1 point. Okay? They cut off, or sub 10. That's the second point. Okay? 5 360ths. That's the third point. And then of the circle circumference. So 4 points. You have to, if you mentioned the raise of the angle, you got a point. If you mentioned that they cut off an arc, I should say cut off an arc. Okay, so raise is 1 point. That the raise cut off, that's 2 points. That it's cutting off an arc, that's 3 points, an arc. 5 360ths, that's the fourth point. And then of the circle circumference, that's the fifth point. So it's worth 5 points. Okay? Same thing. But the only difference is, instead of 5 360ths, it is, what is it, 5 what? Radius lengths. This is where openness in radians comes from. Cutting off 5 radius lengths. So, raise, 1 point. Cutting off, 2 points. Arc, 3 points. Or that's the third point. 5 radius lengths. That's the fourth point. And the circle circumference is the fifth point. Okay, what about 5%? Yeah, you could say the only difference here is going to be 5% or 5 100ths. Raise, 1 point. Cutting off, second point. An arc, third point. 5 100ths or 5%. Fourth point, circle circumference, fifth point. Okay, so what do we do on Friday? If it's 5 radians, we started by saying, start by going to the percent of the circle. What percent of the circle, or what fraction of a circle circumference is 5 radians? 5 over 2 pi. So that's the fraction of the circle circumference, that is 5 radians. And then we want that fraction of what? To get degrees. You're going to take that fraction of 360. See, the first number is the fraction of the circle, and we want that same fraction of, or same percent of 360. Who's got a number for me? Okay, this right here, that's 2 points. So 5 over 2 pi. You got 5. If you had 5 over 2 pi, that's 2 points. Times 360 is 1 point. So this problem's worth 3. So if you just had that first thing without the answer, that's full credit. So 2 points for the fraction, then an additional point for multiplying that fraction by 360. So what is this out of? 18? Yeah, I can't go through all the grading. You want to grading it? Grading?
No, I just was wondering about the answer to number 2. Why would it be of the circle's circumference? Because you're measuring it in radius lengths. You're not actually basing it off of the circle's circumference. For the other two answers, we're based off of the circle's circumference and measure the length. So
but it has to be radius lengths on the circumference. It can't just be any radius lengths.
But if it's radius lengths of an arc, would that not be applicable?
So okay, maybe I'll be better on. Yeah, so where those radius lengths are is important. So yeah, so that's a good point. So instead of, so on. So radius lengths on the circumference. Okay, any questions, not about grading, but about the ideas? And so if you didn't do well on this, you need to, okay? So you need to be able to articulate what angle measure means, okay? So the whole next month, most of the rest of the semester is going to be about trigonometry. Trigonometry starts with really understanding angle measure really well. So that's why I did this. So maybe we'll do a similar thing in the future, okay, in a week or two. And everyone gets 100 then, right? Everyone gets 100. Anybody have a question? Okay, put your score at 18 on the top. Pass it to the center aisle. Please give Jerome a clean left edge. Take the no party favors, right? Clean left edge. Make sure your name's on it. Okay, so we've been talking about looking at these circles, and so we said this over here, the positive x-axis is we're going to call that the 3 o'clock position, or so like this point right here, the 3 o'clock position. And from there, we're going to sweep angles counterclockwise. We're going to sweep angles counterclockwise. So let me start over here. So there, from the 3 o'clock position, we sweep counterclockwise to the terminal side. Then that terminal side will determine a arc length, right? If we measure that arc length in radius lengths, we're measuring the angle in what unit? We measure that arc length in radius lengths. We're measuring the angle openness in radians, right? That's what radians is, the number of radius lengths cut off by the rays of the angle. So this is going to be where we live. The angle swept counterclockwise from the 3 o'clock position. We're going to say it a million times. The angle swept counterclockwise from the 3 o'clock position. And so as that terminal side sweeps around, we get quadrants, right? This is the first quadrant. Second. Well, that's interesting. That's weird because it's in the wrong signal. Right now it's selected the classroom computer, but I'm not complaining. Okay. All right, so that's the second quadrant. Third. Sorry to disappoint you, it works. Fourth quadrant, okay? So, and then when we put this circle like this with the center at the origin and with a radius of 1, so you can't really see that very well, but this has a radius of 1. So circle center origin. And the radius equals 1. That has a name. It's called the unit circle. So when we declare that the circle is centered at 0, 0 and has a radius 1, that makes it sound like it's a very specific circle. Like only this circle is the unit circle. But I want to totally turn that on its head, and because we want to think about the unit circle as every circle in the universe, every circle in the world, every circle in the U.S., every circle in the galaxy, every circle. Okay, so how can we think if it has a radius of 1? So suppose we're talking about a Ferris wheel. The Ferris wheel has a radius of 36 feet. So, what are the coordinates of this point? 36, 0. Okay. Is it the unit circle? Does it have a radius of 1? Well, it has a radius of 36 feet, but we want to think of it also having a radius of 1 as well, both. How can that Ferris wheel with a radius of 36 feet also be thought of as having a radius of 1? What would the 1 stand for? Yeah.
100% of 36 feet.
Okay, 100% of 36 feet. So what is the 1? 1 what?
Your units are 36.
Okay, so your units are the radius, right? So 1 could be 1 radius length, right? So if it's 30, so then in that case, in this particular, the Ferris wheel, that 1 radius length happens to be 36 feet. But the 1 stands for 1 radius length, okay? So then, you know, we're some orbit in space, and some planet has a perfectly circular orbit, and it's, you know, I don't know, 8.8 billion miles. I don't even know if that's realistic for the orbit, the radius of the planet. Something in space has a radius of 8.8 billion miles. How can the radius be thought of as 1? 1 radius length. And so in that case, 1 radius length is equivalent to 8.8 billion miles. So the unit circle isn't one very specific circle. We can think of it as every circle where this unit of 1 stands for just how long the radius of your circle is. How many radius lengths? 1 radius length. And we know that coincides nicely with our radian angle measure, right? Because we measured in radius lengths as we went around. Okay, so up here, how many radius lengths up are we from the horizontal diameter? How many radius lengths up from the horizontal diameter are we right here? 1, right? The coordinates of that point are, a trick question. Okay, so here, right here, this is the point, this is halfway up. So if we come over here, look at this point right here. So on the Ferris wheel, how many feet are we above the center horizontal diameter here? How many feet up are we on the Ferris wheel? We're 18 feet up, right? Because it's how many radius lengths? Half. This is half a radius length here. So if it was on the Ferris wheel, and the Ferris wheel stopped right there at that point, we would be 18 feet up from the horizontal diameter. Okay? If it was our circle and whatever this thing that's going around in space, how many billion miles is it above this horizontal diameter? 4.4 billion miles. In both cases, though, you can measure it as 0.5, right? You see that? So it's 0.5 radius length. So this is how we're going to, when we talk about the unit circle, so yes, it's center 0, 0, radius 1, but it doesn't represent just one very specific circle, it represents every circle. And the units of measure are radius lengths. If you measure everything in radius lengths, then it can represent every circle. Okay, anybody have a question on that? So open up to, I think it's investigation 3. Module 7, investigation 3. Is it talking about a bug on a fan? What page is that? 267. Okay, and what is the first question that asks? All right, so that's the context. We're not going to do those questions though. Okay, so if we start there from the 3 o'clock position, suppose that the bug sweeps out. Oh, so the radius of the fan is 2.6, is that right?
Yes.
2.6 feet. So how far is it then to the right when it starts at the 3 o'clock position? How far is it to the right when it starts? So some of you said 2.6, which is correct if you're talking about feet, but we could also say it's 1, right? It's starting 1, what, radius length to the right, okay? So now it's going to travel 5.2 feet. Puts it right about there. And then we're going to pause the fan, okay? So it started at the 3 o'clock position, traveled 5.2 feet. So I want you to talk with the person next to you. How many radians did the fan sweep out and why? Okay, how many radians did the fan sweep out and why? Go talk to the person next to you. Okay, Colton, what do you think?
2.
How did you get 2 radians?
Because 5.2 feet is twice the length of
Okay, so 5.2 feet is twice the length of one radius, right? So if the radius is 2.6 feet, how many radius lengths did he travel? 2, right? So how could we set up a calculation that gets us that 2 radians? Yeah, so it'd be you basically asking how many radius lengths fit into 5.2, right? How many radius lengths of 2.6 feet would make up the full arc of 5.2 feet? So remember that's our full arc length in feet. That'd be S over R. And so what is S over R doing? It's counting how many radius lengths make up that arc length. This is how many radius lengths are equivalent to what? S or R? Right, equivalent to S. And that's what we know what radian measure is. How many radius lengths equivalent to S? So that's why to get theta you divide S over R, because that would give you how many radius lengths are the same. How many lengths of R units fit into whatever arc length S you have. Okay, so now the bug is going to go 11.7 feet. That puts them right around here. 11.7 feet instead. How many radians did the fan turn? How many radians did the fan turn from the 3 o'clock position? What'd you get? He said 4.5. Eric, you said 4.
I was going to ask if you could repeat what S over R is. I can't really read them.
How many radius lengths are equivalent to S? You couldn't read it, but you knew it, right?
Yeah, I just wanted to clarify.
Yeah. How many radius lengths are equivalent to S? Okay, how'd you get 4.5?
Arc length divided by radius.
What's that?
The arc length, the total arc length so far,
Yep.
divided by the radius.
And why does that work?
Because, well, that equation is S equals R theta. So switching it equals theta. So that's
Yeah, but why does this work? So why does that accomplish what we want? Rather,
it's in radians.
Okay.
So the number of radius lengths. So you're dividing the total number of radius lengths done by the actual radius length.
the total number of
Radius lengths on the arc.
but 11.7 is not radius lengths, right?
What's the arc length divided by the radius lengths?
Right, to get right. Yep, so this is the total arc length in feet, and we're asking how many 2.6s fit in 11.7, right? And that'll be a number of radius lengths, and that's 4.5 radius lengths, so it's 4.5 radians. Okay, so now that's kind of review, talking about radians. So what we really want to talk about is the location of the bug after sweeping some angle. Okay, so the location of the bug after sweeping an angle, theta. So we can find out how many, we can, given the number of feet, we can say how many radians it's gone, but that's not the most convenient thing for in terms of like pinpointing where the bug is after a certain angle measure. So what kind of quantity would help us pinpoint the location of the bug? Any ideas? How could we want to nail down, like, so we pick an angle, and then that determines a location of the bug, and we want to quantify that. We want to measure where the bug is. How could we do it? Jeff?
We use the properties of the unit circle.
But what quantity do you want? I'm asking about what quantity. What's that?
Use a triangle as 1 unit by 1 unit.
A triangle.
And use the radian corresponding x and corresponding y.
Okay, so when you say that, say the y, what do you mean by the y? What does that mean?
Elevation over the vertical diameter.
Okay, yeah, okay, horizontal. So if we think about the horizontal diameter, we can think about how high above or how far below the horizontal diameter that the bug is at any given angle. Okay, so it's supposed to say horizontal diameter. Where did it go? Oh, it's gone. So we call this the horizontal diameter. Okay, and so we're looking at, like you said, all right. You see that red line that I'm showing there? That's showing a vertical distance above the horizontal diameter. This is going to be a key quantity for us. Does that alone pinpoint the location of the bug? So if I pause it here, does that tell us exact? So now we're going to measure this distance right here. And that distance will actually be negative. If we define this as above the horizontal diameter, this is below, so it would be negative this distance. Does that pinpoint the exact location of the bug? No, because it could be anywhere then along this line that has that vertical distance from the horizontal diameter. Okay, so you imagine anywhere along that. So you come along here, and like later, the bug has that same, like that. Later on, it's in that same, it has that same vertical distance. Okay, so that on the circle, a vertical distance could define two different points of the bug. So how do we pinpoint? Yeah, so then we can show, likewise we can show the vertical diameter. Maybe I have to have the circle on. That's what it is. No, I don't know where to go. So we could show the vertical diameter. And we could talk about what quantity?
Horizontal distance.
Horizontal distance? Okay, so we got to be specific because we could be, just like we said above, that would be above is positive, below is negative. So we're going to say the horizontal distance to the right of the vertical diameter. Now, if we knew those two, say for this location of the bug right here, so I can show that red line. So now I'm showing this red line here and this red line here. So this red line is showing vertical distance above the horizontal diameter. This red line here is showing a horizontal distance to the right of the vertical diameter. Do these two together locate the bug, pinpoint the location of the bug? Right. Okay, so if we have, for a given angle measure, if we have the vertical distance above the horizontal diameter and the horizontal distance to the right of the vertical diameter, we have nailed down where the bug is. Okay? And then that location, those two quantities will change as the angle changes. Okay, so this is the idea of a function, right? Input is, this is the idea of a function. What's the input? What's the input? What's that? The horizontal diameter is the input. Distance from the horizontal diameter is the input. Agree with that? The angle is the input. So what comes first? So remember, with functions like that input quantity, the input independent quantity is kind of like the thing we have control over, the thing that comes first. So what do we think?
Radius length?
Which radius length? I mean, you got to be specific, right? When we define a quantity, you got to be specific. There's lots of different radius lengths we could measure here. Yeah.
The distance on the 3 o'clock line, like, like the distance on the radius that starts on the 3 o'clock plane.
Okay, so what kind of distance?
Depends on the measurements you have.
Like, which way? So you got to define, be specific. What measurement are you talking about? What distance are you talking about?
From the center point to the right side.
So that doesn't change, right? That's always constant from here to here. You're saying from here to here?
Yeah.
That's the input? That always stays the same. That's always our radius length. So if we're talking about figuring out where the bug is at for different inputs of what? So, yep, so, and you also said angle earlier, right? So either ones. So you could say from an arc length, you could say the arc length, pick an arc length, and then we're going to output, we actually have two different functions, right? We're going to output a vertical distance and the output of horizontal distance. That's two functions that have this input of either arc length, or you could say the input is angle. Okay, and so these are these. So the input, we want the measure of the angle swept counterclockwise from 3 o'clock. And then the output is going to be, so here's one function. The output could be the vertical distance above the horizontal diameter. And then we could measure that in feet, say if it's the fan, or we could measure it in radius lengths like we talked about before. Okay, so let's talk about this function right here. So we want to use our covariation reasoning to figure out what this function would be like. And who remembers our covariational reasoning? What was our approach to reasoning about how two quantities change together? What do we do first? Oh, someone knows. Tell me. Who was it?
So, for small incremental changes in the input,
Right.
the reaction to the output.
Yes, thank you. Someone knows. Good. Hopefully others of you were thinking that. You look at small incremental increases of your input, in this case, which is, what's our input?
The angle swept counterclockwise from the 3 o'clock.
Measure of the angle. Measure of the angle is the input. So we're actually look at these small increments right here. Boom, boom, boom. See those little dots? Okay, and then we see what we ask questions about the output. What was the first question we asked about the output when we look at these small incremental changes? Do you remember? What's that? What question do we ask about how the output reacts first? It's the easy question, right? Yeah, does it go up or down, right? So when you do this, each increment of your input variable, does the output go up or does it go down? And so what's our output? Vertical distance above the horizontal diameter. And then our next question that we ask? Then we compare each change, right? We look at each change and we say, how does the current change compare with the previous change? Is it bigger? Is it smaller? Is it the same? Are these changes increasing? Are the changes staying the same? Are the changes decreasing? And then from that, we say we can talk about the rate of change. And then to help us with that second question, we can ask if the changes are becoming more positive, more negative, less positive, or less negative. That's to help with number 2. Okay, so here's that summary of how we reason about two quantities covariationally. Okay, so and there's our input and output up above. So first of all, so what increment of angle am I choosing here if I use these little tick marks? So I want everyone to figure that out. So if I'm going to go equal increments of angle, so that 4 take me up to the top, 8 take me halfway around, 16 take me all the way around. What is my angle increment that I'm choosing to be my small equal increment? Everyone figure that out. Talk to the person next to you. What would that be? Okay, what's my equal increase? What do you think? Matt thinks he's got it.
Pi eighths.
He wants pi eighths. Agree with that? John does? Michaela, you're making a face. You agree? You sure? Where does that come from? We know that how many radians exactly halfway around? Pi. Right? So three radius lengths or 3 radians is almost halfway. And so then to get exactly halfway, it's this irrational number pi. It's the number of radius lengths to get us halfway. So then a quarter of the way around the circle, pi halves, and I'm going to break that quarter circle up into 4 equal pieces. So we got it. That's right. Our increment is going to be pi eighths. Okay, so here we go. I'm going to take the first pi eighth, like this. Did the output, the vertical distance above the horizontal diameter, did it increase or decrease? Increased, right? Because the bug's going up, so it's higher above the horizontal diameter. Next change. Did the vertical distance above the horizontal diameter increase or decrease? Okay, so that change is positive. Is it more or less positive than the previous change? More positive. Agreed? All right, next change. Positive or negative change? Positive change. Is it more or less positive than the previous change? Oh. So here was the first change in the bug's vertical position from here to here. So let's focus here. And then the next vertical change was from here to here. And then this third one was here to here. These changes are positive because that vertical distance is increasing. Are those changes getting more positive or less positive? Less positive. People are still saying more positive. This is the largest change right here. And then this one's a little bit smaller, and this one's a little bit smaller. So the vertical distance is increasing, but the change in vertical distance is decreasing. So when the changes are decreasing, the rate of change is decreasing. So is our graph going to be concave up or concave down? Someone said down. Agree with that? So the graph, so what is when the angle is 0, what is the vertical distance above the horizontal diameter? 0. When we make that first eighth the change of an angle, the vertical distance goes up. When we do it again, it keeps going up, but it goes up a little bit less than it did before. The change is positive, but less positive than the one before, and subsequently with these last two. So the graph is increasing, but the changes are decreasing, which means the rate of change is decreasing, and the graph is concave down. Concave down. So that's the first quadrant. It's the graph we get for the first quadrant when we're measuring the vertical distance above the horizontal diameter. We'll do it on Wednesday.